No, this is hours. So I know that everything's working just fine from here to there to there.
Why did you move it to CME1?
Just to test it.
Oh.
has a number of research grants, and principal investigator in a number of ongoing projects. It has more than 50 publications, and we're happy to have him today.
Thank you very much. Thank you. Okay, so yeah, I just moved the college of medicine to July 1st. We're here for 5 weeks. And it's amazing just moving your lab across all the way across the street. This is a closure, of course, the financial interest, which I have to say is that, obviously, not financial interest. You wouldn't mind that. All right, so this is important. 45 years ago, August 7th, 1970, something called the Marion County Courthouse, Incident, California. It was a Friday. It was the day I was born. All right, so this is my birthday. I'm halfway to 90. That's a little town I'm from. Notice it's called Pickup. Is that happy to be nice? All right. First of all, I always like to start off with acknowledgments because basically you get to the end of the talk, you seem to always never have time to truly acknowledge everybody that really makes this work. You don't. People that do science and do neuroscience know this doesn't happen alone. So first of all, Dr. Matt Palmatier, who I recruited from Kansas State. He's in the Department of Psychology here at ETSU. He's my partner in crime, colleague, friend, and really important in doing some different things with this particular model and taking it to the level. Dr. Rich Kostreva, who's in my Department of Biomed Science. Dr. Kostreva actually is one who came up with the neonatal criminal model that we use, and he's always been a good colleague at Big 2, who's also in our department and does some viral vector work for us. Importantly, I'll point out all my graduate students there, former grad students currently. I think everybody there is in a postdoc. Amanda Maple looks like she's a lounge singer there. But she was doing a presentation there. She's a postdoc person here in Silver. And then my current graduate students, Beth just got her PhD in Nebraska. And then my current and former undergraduates, Bob. Okay, so we're going to focus in on schizophrenia. When you talk about modeling schizophrenia in a rodent, that is not something that is easy to do. And it's amazing how many models there are, but it's certainly something that's difficult. And so one of the things with schizophrenia, of course, it affects about 1% of the population. The slide Here's your positive symptoms: auditory hallucinations, delusions of grandeur, disorganized speech, paranoia. How are you going to be able to model that in a rat? That's fairly difficult to do. And I don't think there's any positive symptoms that behaviorally are going to do very well. But negative symptoms you can pick on, and basically that's cognitive impairment, which we're going to show, social withdrawal, which we've seen on some different measures I'll show here, and anhedonia, which is also very important. And so really, when you go into this, what you're trying to do is you're trying to model a very complex disorder. You're going to do that with particular manipulation, and then start looking at the cellular, plasticity changes, behavioral changes, hopefully that are all. So there are 60 models of schizophrenia. So it's not like people aren't trying. Okay, we're trying to get to a good model of schizophrenia. Probably the most accepted, most prevalent model, neonatal lesion model. This is where basically a 7-day-old rat and produce lesion in the hippocampus. That's fine. There's some behavioral validity there. This is with Barbara Lipska, Daniel Weinberger, intramural surgery at UNIV. But the problem with it, of course, is that there's no cell death. Okay, cell death does not occur in the hippocampus in schizophrenia. Their hippocampus is changed, but it is smaller. But there is no defined cell death. I always use the quote from my friend and colleague, chair of pathology, John Schweitzer, who always tells me, he goes, schizophrenia is the graveyard of neuropathology, okay, to find cell death. Another prevalent model, there's some other models like the Q drug models. I mentioned this one, the PCP model. That's a good psych. Antagonist, increasing the dosage level. That's been shown to have some good behavioral validity when the animals that are close to them. But there's multiple genetic models like DISC1, which I didn't put up there, but which is a mouse. But the thing is that basically everybody's doing some different things relative to trying to manipulate. One of the things that the advantage of the genetic model obviously is neurodevelopmental, and that's something that is really important because the DSM actually refers to schizophrenia. So what do we do? So basically this is a developmental model. This is what we do is when rats are born, we give them a drug called pimperol. Pimperol is an agonist, so activates, binds to dopamine D2-like receptors. Are the different subtypes. So Strava has shown in a number of papers, he actually originally discovered this in 1990. Post-numbers 1 to 21, 11 to 21, 21 to 35, all those all produce an increase in dopamine D2 sensitivity, and it persists throughout the animal's lifetime. And the way he measured that, at least at that time, was to do a simple test called the Yawning Test, which I'll show you here in a second. That's right, yawning, which is a D2-like mediated behavior. But that's his, he has a couple of review papers in 95, and then again did one in 2008. So to explain a little bit more about the dopamine system, dopamine binds to two different families of receptors, the dopamine D1 and the dopamine D2. And obviously, it's in red there to indicate that we're focusing in on the D2. And this slide I got from NIDA, National Institute of Drug Abuse, which actually funds our grant. And I just want to focus on the yellow pathways. Those are the dopamine pathways. But this is really one of the best figures I could find. It really kind of denotes where dopamine is located in the brain, where it projects to. Okay, so we have cell bodies that are in the substantia nigra and the ventral tegmental area in the midbrain. And they project forward. And they project into the striatum, okay, very large area of the forebrain. It projects the VTA, projects ventral tegmental area, projects into the nucleus accumbens, which is your reward pathway. The pathway from the substantia nigra to striatum, of course, is a nigrostriatal pathway involved in a lot of motor function. Then there's also very important projections that come into the frontal cortex, also from the VTA. And this circuitry basically underlies things that are related to drug abuse, like reward, motivation, pleasure, euphoria, all those things. Motor function, obviously, the striatum, otherwise known as the basal ganglia, the fine-tuning of motor function is really its role. Also things with compulsion and perseveration. So the dopamine system's, of course, been implicated in other disorders. And one of the things I want to talk about is that although I think we have a pretty decent model of schizophrenia here, this model actually converges, it really kind of can go out to even other types of behavioral disorders that are related to dopamine dysfunction, including things like bipolar or obsessive compulsive disorder, which also kind of converge around the dopamine D2 receptor and changes in it. So when I got recruited to be on the editorial board of Developmental Neuroscience, Greg Stanwood has been a collaborator of mine. He's at Vanderbilt, and he just left Vanderbilt, went to Florida State. But Greg came by our poster presentation at Society for Neuroscience, I want to say 2005 or 6, and said, we want to get involved with doing some collaboration with your, we really like your model. We think your model has some real relevance. I was like, oh, that's cool, whatever. So we talked about that, and we'll talk about some data we ran in a paper we published together. But as a result of that collaboration, he invited me on the editorial board, and then I got invited to give this review paper. And this kind of denotes everything we've shown, and this actually isn't even all completely up to date. We have some new data that I'll show you today that's actually relevant to a model of schizophrenia. And really, basically, we've been working with this since I got here, and I arrived at ETSU in 2000. And I really want to point out, I guess it's box 4, let's see, what is that? Box 5 and 6 down there with the olanzapine. One of the things that's critical about a model of any disease, if you're going to try to model it, is that you need to be able to treat the animal, if you're going to do a rodent model, is to treat the animal with something that actually works to alleviate behavioral deficits in that model. And so we were lucky enough to get a grant from Eli Lilly for about, I guess that was 2003, around that time, to about 2006, to look at some effects of olanzapine, which of course the trade name there is Zyprexa, very common atypical antipsychotic that is prescribed to schizophrenics. We showed that it reversed cognitive impairment. We showed that it also reversed decreases in neurotrophins that we were studying. And so that was a really big set of studies that we did. We published both of those, and those were good to be relevant. So I think that's something that's very important relative to our model. We have shown some other things, and I'll go through there. Those, basically,
not so much the cognitive impairment, but more relative to a focus towards drug addiction. Because our current grant, we're focused, and we have been funded through NIDA pretty much since 2007 to look at drug addiction in this model. And one of the things that's most prevalent in schizophrenics is they smoke cigarettes. And they smoke them heavily. And so the thing is, nicotine addiction, obviously a major health concern, we know that. Schizophrenics are roughly 4 to 5 times more likely to smoke than the general population. And the one thing with schizophrenics is not just that they smoke them heavy. One after the other, okay? Its quality of life is poor. They die earlier, okay? There's a lot of basically damage to the lungs and to the pulmonary system and everything else that occurs with that. So they are very much more likely to smoke cigarettes, and no mechanism has ever really been identified. There's always been this approach from the Friedman group out of Colorado, which I think they do some great work. I'm not trying to rip on anybody here, but they always have really focused on the cognitive dysfunction and the things that are related to the cognitive dysfunction. And cognitive dysfunction has been related to sensory gating, which I'll talk about here in a second. But there's also kind of another camp, and they don't necessarily go against each other, because maybe both, right? And one of the things that has been really an approach is the alleviation of anhedonia. Is that this is a self-medication in some respects. I mean, in a lot of respects. And that, I think one of the critical things about, and what's been self-reported in schizophrenics is that, this anhedonic, those negative symptoms are very aversive. They don't like that, right? And so they smoke. They do things to try to get away from that particular symptomology. And that's true of a lot of different disorders. I mean, you get into depression, bipolar, and other things like that. There's no doubt that there's self-medication that goes on. I don't think that many would really argue about that. I show a couple of epidemiological slides here. This is Callahan, Journal of Psychiatry Research, looking at tobacco-related deaths and these different disorders. But what's really, you can see there, schizophrenia and bipolar depression, all much higher rates of smoking in those populations, and then you get the tobacco-related deaths with that. And so we're going to really focus on when nicotine use starts. We think that's a real critical piece, because the thing is that adolescence is a critical period of development that has really, to be honest, in the animal world of addiction, and the research that's gone on, has kind of been ignored, okay? That's been ignored, and gender differences / sex differences, sex differences, you're talking about it in rodents, has really been ignored. That's one of the reasons why NIDA has a real big focus right now. One of the big priorities is adolescent, work with adolescent models. So that's obviously a critical period of development. There's a lot of really critical changes in the dopamine system during this time. There's big sex differences in rats and in humans that are different relative to dopamine receptors. I won't go through all that, but Anderson and Teicher, Susan Anderson's up at Harvard, has done some really nice work on really detailing those changes in receptors, changes in neurotransmitters, or to change in the neurotransmitter through that period. And nicotine use obviously typically begins in adolescence. That's when it starts, okay? With most people. And adolescent smokers that are schizophrenic, you can see here that, and I talk about, how much it's not just that they smoke, it's how much they smoke. And you can see they're greater than 10 cigarettes smoked today at age 18, and obviously the prevalence of schizophrenia is obviously that much higher. And that goes with any behavioral disorder, okay? So the thing is that one of the things that's kind of a misnomer about schizophrenia is that it's a neurodevelopmental disorder. DSM has said that, has stated that, it's in there, okay? So the thing is this doesn't just, when they get full manifestation of their symptoms at 22, 23, 24, that's when it shows up. They were normal before that. No, they weren't, okay? It has a really good hereditary tie, and so it exists before that. There's different elements of that, and it probably has to do with, at least several theories are that, the brain's not fully developed until it's roughly 21 years old. So 22, something like that. So the frontal cortex is actually full in development. So I'm going to show you some data. So this is really work over about the past 7 or 8 years, I guess. Some of these references go back that far. To show you some things that we've done with this model and where we're going. This within the preliminary data, this is really going to be preliminary data for a grant. We're hoping to go in with an October 5th, but, which is the R01 deadline. But so everything here that we do is we give the quinpirole 1 milligram per kilogram. We give it once per day for the first 21 days of life for the rat, okay? We know that that works to increase dopamine D2 sensitivity throughout their lifetime. Dr. Stravis showed us that throughout their lifetime. We've certainly seen a lot of effects of that. So we know that increases the dopamine D2 receptor, and that works, and so that's the period that we chose, and we've done that with a lot of our work. We're going to look at several different behavioral tests. I mean, I'm a behavioral neuroscientist / behavioral pharmacologist, so we do a lot of behavioral testing in my lab. So everything kind of focuses around behavior, and then we go after neuroplasticity and underlying mechanisms beyond that. But we're really going to look at sensitization, condition place preference, sucrose preference, which is actually a little bit different way to do that, and then nicotine self-administration. I'm also going to add in there, I added one slide in here, and the prepulse inhibition, which I'll talk about. But basically, sensitization is just that we give the drug every other day. We basically give the animal the drug, we inject it in intraperitoneal, which is in the peritoneal cavity, get a nice little spike in the content of the drug in the brain that way. So we'll look at sensitization, that's just a locomotor activity change. Condition place preference is a really nice way to look at the rewarding associative effects of drugs. Because one of the things that's really critical with nicotine, it's critical with a lot of drugs, rewarding drugs, but they get associated with a cue. They get associated with something else, okay? How many smokers do you know that drink, right? I only smoke when I drink. That's what they call a chipper, right? But they associate that with that. Or smoking with coffee, or smoking with some other cue. So basically, that's condition place preference. What we do is we just condition them to prefer a place in a shuttle box. And I'll talk about that. It's a very common type of behavioral test. And then the sucrose preference, which is pretty, that's straight up looking at preference for a natural reward. And then we'll look at nicotine self-administration as well. So one of the things that, if you're going to look at increases in dopamine D2 sensitivity, this has been done a lot, is to do a yawning test. And let me tell you, if you're running a behavioral neuroscience lab, and you really want to get all those really good undergraduates out of your courses, you say, we study yawning. And they just go nuts for it. So they're like, can I go study yawning? Okay. Anyways, so what you do in this behavioral test, you neonatally treat the animal with quinpirole. We raise them to adulthood, and we gave them 1 injection of quinpirole. And it turns out that yawning in the rat and in humans is mediated by the dopamine D2-like receptor. Whether it's D2 or D3 has been argued, and Cooper and Collins argued about that. We weren't actually all that interested in whether it was D2 or D3. What we did get, though, is when we gave them our acute quinpirole, we got a big increase in yawning. And we got a very interesting sex difference that existed. Males yawn more than females. I don't know what that says about males, but we got that. And it really, the thing is, I think it's critical here is that you just get an increase in that yawning test, or in the number of yawns in an hour, and basically is how we do that. And Rich has shown, Schizophrenia has shown that all the way out to 2 years. So, rats live for about 2 years. So he's got it all the way through their lifetime, and they show the same effect. It's a little bit less in magnitude, but it's still there. But when we did that, I presented that, probably in 2004 or 5 in the College of Medicine, one of the seminars over there, and I said, it'd really be nice if you could do some type of cellular mechanism of increases in dopamine D2 sensitivity. About that same time, maybe a little bit later, Greg Stanwood is the guy I mentioned from Vanderbilt that came by our poster, and he said, let's try to find a cellular mechanism. What should we go after? And he came up with RGS9, which is regulator of G protein signaling 9, which actually is on the dopamine D2 pathway. Dopamine D2 receptor, that family of receptors, is a G protein coupled receptor. And RGS9 is a protein that regulates that G protein cell cascade. And so the situation is that RGS9 is decreased post-mortem in schizophrenics in a big way. We got the same thing in our animals when we actually went in and sectioned the tissue. These are animals that were given quinpirole, 1 to 21, grown to adulthood, and then we showed that RGS9 was decreased, in our quinpirole animals, which is what you'd want to see. This is a regulator, okay? The regulator is basically being inhibited, or is basically there's less of it that is present to work. So therefore, we got about a 200 to 300% decrease in RGS9 in in brain areas that receive the dopamine projections, as I mentioned on that earlier slide, the nucleus accumbens, the striatum, and the frontal cortex. And we got it across all three areas. Seaman in 2007, others have shown in schizophrenics post-mortem, there is decreases in RGS9. They've shown the hippocampus, they've shown the striatum, frontal cortex. I don't know if anybody's looked at nucleus accumbens, but it is there. Okay, so we published that, European Journal of Neuroscience in 2007. So that was one of the things that was really important for our model, is that we could show that it was not only a behavioral increase in dopamine D2 sensitivity, there was a change in RGS9 expression. So we had actually, that's a genetic consistency. Marla Perna, when she was in my lab, was a PhD student in biomedical science. I was adjunct in that department, so I was able to train her. And we ran this study here. This is a behavioral sensitization study where animals were given neonatal quimperol and then sensitized to nicotine. And so what we did here is we gave them nicotine every other day in adolescence. Okay, first of all, I don't know if I mentioned this, but adolescence in a rat is about personality 30 to 60, their second month of life. Okay? Before that is considered to be equivalent to brain development in a human that would be more pre-adolescence. Okay? So 30 to 60, that's relatively agreed upon in the literature. There's a little bit different periods, but it's all based on hormonal, behavioral things like play behavior and things like that. But basically what we did is we wanted to do a dose response with behavioral sensitization. So we did use a 0.3, 0.5, 0.7 dose of nicotine. That's all free-based dosing is the way that's calculated. We got a really big increase in responding to the 0.7. We got enhanced sensitization to the 0.5. And the 0.3 gave us a little bit different type of result. But the bottom line is that really the bottom of the take home here with this fairly complex graph that we published in Behavioral Brain Research is that neonatal quimperol enhanced behavioral sensitization to nicotine. Okay? Behavioral sensitization has been shown, across the literature for many years by Peter Kalivas and Terry Robinson and big names in the field, that this is a dopamine-mediated behavior. In other words, if you go in and you block dopamine receptors, you block D1 or you block D2, you will reduce sensitization. Okay? So it's been shown to be mediated by the dopamine system, and especially in the nucleus accumbens and ventral striatum really being the areas that mediate this behavior. It's fairly simple behavior, and all that we did was we gave the animals the injection, and we looked at locomotor activity. How much did they move? Okay, we have a really nice behavioral scanning system called AnyMaze that does that automated now instead of having to count that the way you used to have to count it with a little clicker, which stinks and is hard to do. So what we did is, since we showed that the 0.5 dose, those animals were sent to all these Kalivas, Robinson, and this group, the research literature says, well, dopamine mediates it, that we should be able to see an increase in dopamine release in a brain area that mediates behavioral sensitization. And we got that. Okay? Big increase, 500% increase relative to controls that got nicotine, and the controls that got nicotine showed about a 250 increase relative to baseline. So nicotine increases dopamine, no doubt. Dopamine's involved in reward. Okay? Nicotine is a very interesting type of stimulant in the fact that it's not cocaine, it's not amphetamine. Cocaine and amphetamine, we actually ran the same study with amphetamine and got like an 800% increase in our neonatal quimperol levels. Okay, that was published a few years ago. We actually had a grant to look at amphetamine in this model. But with nicotine, it's such a more commonly used drug in this population. This was something that we really were happy to see, and that's the 0.3, 0.5, 0.7 arrows there, or when we actually did what's called a cumulative dosing curve, where you give them 0.3 in the first injection, and you give them 0.2 and 0.2, so you accumulate to 0.7 through that time period. But we got a nice big increase there in dopamine release. The other thing I mentioned was conditioned place preference, which was a rewarding associative effects of the drug. So when you conditioned place preference is actually pretty tricky with nicotine. It's not tricky with cocaine, amphetamine, morphine, these really big, really crank the dopamine system, and you can really get nice conditioned place preference. Conditioned place preference is simply that you inject the animal with nicotine and put it into one side or the other of a shuttle box. And that shuttle box has different tactile, different patterns on the walls, okay? And it has these removable dividers in between those contexts. So you put them into one context where, for example, it could be vertical. The other context might have horizontal lines on it, okay? And the vertical, it might have a chicken wire floor, and the other one has a little dowel rods. But the bottom line there is that you condition them. So this is conditioning for 8 days. You have to give them 8 consecutive days of nicotine. They get nicotine in one context, they get saline in the other, okay? And then the saline controls get saline in both. And these particular groups refer to the first letter there as the quimperol or saline. That's what they got neonatally. And then the second letter refers to nicotine or saline that they got when they were conditioned. And what we got was, again, neonatal quimperol enhanced the rewarding associative effects. What's key here is that you do that for 8 days, you condition them for 8 days, and then on the 9th day, you take the removable dividers out and you see where they go, okay? So what animals will do is they will go back to the context that they got the rewarding effect in. It's a very clever, very nice drug. It's a drug-free, that's a drug-free test, okay? So that's a rewarding associative effects. It has a lot of classical conditioning elements to it, and that the context refers to the conditioned stimulus, and then obviously the drug is the unconditioned stimulus, and those pairings together work pretty well. So we got a nice effect there, and got an enhancement with neonatal quimperol enhancing the rewarding associative effects. Now I added this slide in. I apologize for adding in any new data, but this isn't really new data, it's kind of old data, but it is a hallmark of schizophrenia is prepulse inhibition, and to give you just a kind of a brief overview of that behavioral test is just if you give an animal a startling auditory stimulus, so it's a 120 decibel click, and then you present them with a prepulse. Then basically at 73, 76, 82 decibel, there'll be like a click. It's kind of like a hiss that comes before a real loud startle. Okay, and they will show you a startle relative to that. It's a behavioral test. The animals are actually in this little cylinder. It's on a little platform, and it records their movement. And so there's actually it records that when that startle goes off, it records that they react. And so what you get across schizophrenics is that you get prepulse inhibition deficits. This is a good behavioral test for what they call sensory gating. One of the things that schizophrenics have a very big problem with is gating, background noise, gating, sensory information, and being able to concentrate on any specific punctate stimulus, something that's in front of them. So that's one of the things that they've said is kind of a root of the cognitive impairment. We've shown cognitive impairment in our model, and we also show prepulse inhibition deficits in this model. We just got a review back on this paper, and it looks like it's going to make it in to pharmacology, biochemistry, behavior, but we're just got to revise it because the revisions are very slight. So we've got a very significant, we actually tested these animals over 10 days, so this lasted over the entire 10 days, and actually we did this, that's just the first phase of it. We did 2 phases of testing, so it lasted over 3 weeks. The animals did get a little bit better at prepulse inhibition, both groups, but quimperol our quimperol animals were consistently showed a deficit. Okay? One final thing here with conditioned place preference on behavior, then we're going to get into some other things. So the thing with nicotine is like a lot of other stimulants. It's kind of an upside down U. In the middle of that U is very rewarding. Before you get there, it's kind of sub-threshold reward. And then if you go over a certain level, it becomes aversive, okay? So an aversive dose in a rat is about 1.8. And 1.8, so what we did here is a conditioned place preference, just like I explained before. But neonatal quimperol, we did get the nice thing where we get the enhancement of the rewarding associative effects of it in these adolescents. These are a little bit older than the other ones we tested. But what we saw, what was very interesting, was that in the controls, they showed us nicotine, there was aversive. So when they were conditioned to their particular context, they avoided that context on the drug-free test. They didn't want to go there. The neonatal animals treated it as neutral, essentially. Okay? So they can tolerate higher doses and don't find aversive doses to be that aversive. Okay? So that's something interesting, is a change in the system that's going on there. So we study brain plasticity. So with all these behavioral tests that we run, we always look in the brain to see what the in schizophrenia. Schizophrenia is not just a D2 disorder, disease. There's several different neurotransmitters that are affected. And one of which is there appears to be glutamate receptor hypofunction. Whether it's NMDA or AMPA has been argued. But the thing is that mTOR leads to transcription of those AMPA receptors. So we're very interested in that protein to see if there's changes in it. We're going to see that. And then phosphocrab, but we'll look at CREB, which is a regulator that comes out of the cell body here. Cyclic AMP, response element binding protein. And so it actually helps to regulate some of these things involved in cell growth, and it's going to be important in some other types of behaviors. So in BDNF, we've shown this and shown this again. We've replicated this effect. That BDNF also, one of the things that's important to understand is that growth factors like BDNF, and the first one that was ever discovered, nerve growth factor, by Levi Montalcini many years ago, is that these things, they're cell dependent, they're dependent upon cell activity. Okay? So you increase cell activity, you increase BDNF. You increase NGF, where it's located, like in the hippocampus, hippocampal formation, for example. And this is the dorsal stratum and nucleus accumbens. And basically what we see here is that the QN, remember, that's the neonatal quimperol, and they got nicotine. These were animals that were given conditioned place preference. And what we got here, this was with a 0.6, a rewarding dose, is that quimperol enhanced the BDNF response to nicotine in both the nucleus accumbens and striatum. So that would imply that there's more. So one mechanism by which we may be getting increases in dopamine is that you've got an increase in BDNF that's going with it. So when you increase cell activity, you increase BDNF. BDNF increases number of synapses. You have more dopamine synapses, thereby to release dopamine from. Okay? And that's the way you get your increase in dopamine. So we got that in males and females, and there's also there's almost a sex difference there. It wasn't quite there, which is interesting, and there maybe exists if we have, I think our ends there about 6 to 8. And then we also showed there, obviously, nicotine just by itself increases BDNF. Not nearly on the level that neonatal quimperol enhanced it with, but it does increase BDNF, and that's a very, very consistent effect. We've shown that. We've also done this in adults. This was in an adolescent, about post-adult day 50 in these particular animals, but we've also shown that in adulthood. So this is new data. This is only with females, but one of the things that, like I said, we were interested in mTOR and mammalian target of rapamycin, or otherwise known as the mechanistic target of rapamycin. I've seen it both ways. But mTOR, as I said, is involved in transcription of AMPA receptors, also involved in cell growth. And one of the things that is interesting, this was my grad student Daniel Peterson that got really interested in this, and through collaboration with Charlie Stewart and his group, it's been really, really helpful in getting this done. This is with the Western blot. So this is very preliminary data. This is data that we just accumulated. This is actually at 24 hours after nicotine treatment. And these were animals that were sensitized. So this is behavioral sensitization, a little bit different treatment regimen, but bottom line is you're giving neonatal quimprol and you're sensitizing the animals to nicotine in adolescence. And what we got here is neonatal quimprol just decreased it. Nicotine didn't reverse this, okay? But it decreased mTOR. Remember, mTOR leads to transcription of glutamate receptors. So we think this may be a precursor to the change in the glutamate, or we're hoping that we can eventually verify that glutamate AMPA receptors are actually down, or they're showing a decrease in number or decrease in function in our model, which would actually give us not only a dopamine validation, but a glutamatergic validation of our model, which nobody's really ever had. Usually you go one or the other, but being able to get both is very difficult. You notice nicotine didn't reverse it, but Daniel had a very good idea. When I saw this data, I said, oh no, he didn't reverse it. That stinks. He goes, test them at 1 hour. We need to go 1 hour after nicotine. If we go 1 hour after nicotine, because that's what they did with cocaine, that's what they did with amphetamine in the literature. Let's go 1 hour, after we treat the animals the last time for nicotine, let's look at it within 1 hour, because it appears that mTOR does its thing, so to speak, produces changes fairly rapidly. At 1 hour, very preliminary, it's only N of 2 or 3 is what I have right now, but nicotine, the quimprol nicotine groups look completely different. They're going through the roof. They're a big increase. So I think there is a change there that's going on. It's just short in time period, and it's interesting that that mTOR does that, but yet still our neonatal quimprol is dropping it down and is showing a decrease in that particular protein. Now this is also new behavioral data. One of the things that with Matt Palmatier, Matt is an operant guru. He has a bank of like 12 operant boxes or 10 operant boxes in his lab. And it's been really valuable to be able to do these types of behavioral tests where you can go in and you can, an operant box is very simple. The animal presses a lever, or in our case, they actually nose poke. They poke their nose on a little key to get a reward. And he was working on shaping our animals, our quimprol and saline animals. This is in adulthood, post-LA 60 or so, to be able to so if you're going to shape them, you have to train them, obviously, to be able to nose poke. And the way you do that is you give them sugar water, okay? Sucrose, 20% sucrose in water. So, and they love sugar, as you might imagine. And so one of the things that he came to my office one day, he said, this is weird. You guys are weird. These quimprol guys are weird. Well, what do they do? And I was, it's like, well, okay, what do they do? Well, they won't shape as easily. They don't seem to like sucrose. Is there something wrong with their taste receptors or something? Are they dumb? Then I was like, oh, wait a minute. I said, but they're still shaping? He goes, yeah, they're still showing some shaping. They just don't like it as much. And I was like, lights went off. I was like, that's a really good measure, Matt, of anhedonia. Anhedonia is the inability to show pleasure at something that's a natural reward. And that's exactly what we got here. Our neonatal quimprol animals showed us anhedonia on students. This is motivation to press forward. Okay, this is not just, there's a way to do sucrose preference where you do two bottles on the cage and you put sucrose in one and water in the other. And that thing's got its problems because you have to do it at a specific time each day, and there's all kinds of issues with that. This we can actually look at motivation. So they actually have to go over, press this nose poke, and get sucrose. And so sure enough, our quimprol animals were down, okay, and he said, let's give them nicotine. We gave them nicotine, reversed to saline baseline. Okay? This actually supports our entire hypothesis of our grant, which was we think nicotine is being used, or it can be used, to relieve anhedonia in schizophrenia. And then we got it there, and as you can see, we continue to treat them with nicotine, but they are significantly below salines throughout that particular treatment period. So even though they got nicotine, they got to baseline of nicotine on day 1, they still don't reach them even by 5 days of nicotine treatment, and we've replicated that. And that looks pretty nice. And then you see on the left side there is just an overall mean of responding. A good a plasticity measurement of anhedonia has been published by Eric Nestler and Bill Carlozone. I didn't know Bill Carlozone was a old collaborator of Mingyang Zhu, but he told me that the other day. But basically, CREB is cyclic AMP response element binding protein. It is located in the nucleus. It has been indicated in the nucleus accumbens to, if it's increased in drastic amounts, it has been shown to be a really good measure of stress or anhedonia. And sure enough, we got that in this particular measurement. This is with when Marla Perno was still in my lab. She was interested in phospho-CREB because of its regulation and its importance. I'm going to go through all the mechanisms there relative to how it's involved in BDNF signaling. But the bottom line is that Nestler and Carlozone, in a series of studies back in the early 2000s, basically showed that increases in CREB, or in phospho-CREB, which is the active form of CREB, actually is increased in the nucleus accumbens in animals that show decreased sucrose preference, show all kinds of anhedonic actions. And we got that in social defeat stress too, that was one of the behavioral tests they used there. But bottom line is, our QS is our quinpirole salines, and you can see they're very much increased here. So that is a good plasticity indicator that they are anhedonic. And nicotine, the Q and 5, those are animals that were given 0.5 nicotine, show us a reduction relative to that. So nicotine may be, again, used to relieve it. It obviously didn't get to control levels, but it did come down. Interestingly enough, nicotine actually increased it too, just by itself, which I thought was an interesting effect. So this was also a nice measurement. We didn't get the effects, or no, we had a slight effect there in the stratum. But this was a nice effect of nucleus accumbens to give us, not only do we have behavioral measures of anhedonia, we have a plasticity measure that is of anhedonia, and they both go together. Finally, we have been working with nicotine self-administration. So nicotine self-administration is one of the best, probably the best model of volitional administration of nicotine in a rat. Nicotine self-administration is difficult to do because of a number of reasons. One of the key parts of nicotine self-administration is you've got to have it associated with the cue. Okay? So as Matt Palmas here told me, he says, you know, anybody, I could train my 5-year-old kid to come in and train a rat how to do cocaine self-administration. They'll take that in any place. It doesn't matter. Turn the lights off, turn the lights on. They could care less. They love coke. They love cocaine. They love amphetamine. They love methamphetamine. But nicotine's a more difficult animal. It doesn't produce the increases in dopamine that those stimulants do. So you have to put a cue in there for them to associate with it. Otherwise, it doesn't work. Okay, so he did his postdoc, Matt did his postdoc at University of Pittsburgh, with the gurus that figured this out. Tony Kajula, Eric Donnie, Alan Sved. And so they're the ones who kind of got this figured out and what the dose needs to be and that kind of thing. So we started out with our neonatal animals going into self-administration. So what you do is you have to implant the animal with a catheter in its jugular. Then it's going to be able, when it presses that nose poke, it's going to get an infusion of nicotine, IV. So these doses are much lower than what you see, what we inject, obviously, because it's going in IV and going directly to the brain. This is 15, 30, 60, and 90 micrograms per kilogram on each infusion. And so what you do is you set these animals up to, FR, like what's called an FR1, an FR2, and FR5. Those are fixed ratio 1, fixed ratio 2, fixed ratio 5. So they have to give one, and so they start off with, every time they press the nose poke, one behavioral response, they get an infusion. Then they work up to an FR2 schedule, and then work up to an FR5. They have to press it 5 times, and then we also eventually go to a progressive ratio, where we look at motivational effects. Which we got nice effects there, I don't have that data in my pocket right now. But basically, we started out at 60. And this was very much a needle in a haystack, because we were like, what dose do we give them? 30 is the default dose. That's what usually works with nicotine self-administration. We went double that. We got enough, it's very close on both of these, well, at least on the right, on the infusions are, the quinpiroles were going up, but then the active response lever, they were a little bit lower. But the bottom line is, we had a bet, we bet a beer, okay? Which way should we go? I said go lower. Lower didn't work. 30 didn't work. 15, those were sub-threshold doses. We got to 90, boom. They went through the roof. Okay? This is a very high dose. Salines don't really like 90 too much. We're going to now go, we have to get to a descending limit of the dose response curve, because we got about I think it's about 5 times the number of infusions earned, and what is that, about 3 times the number of active lever presses in our quinperol animals at that 90 dose. Now we're going to go to 120. 120 is dangerous for the controls, and maybe for quinperols too, that may induce seizures at that level. But we even saw a little bit of seizure activity here with our neonatal quinperol animals and our saline animals. But the weird thing is, the quinperol guys kept going back. Okay, and we've even got some time measurements on a number of responses, and they seem to bunch their responses much closer together than the salines do, which is very interesting. So we do have enhanced nicotine self-administration in our neonatal quinperol model. So basically, just to do a brief conclusion here, neonatal quinperol enhanced behavioral sensitization, which is a direct behavioral measurement of dopamine activity, if you can say that. I don't know if it's pretty safe to say that. Rewarding associative effects of the conditioned place preference, increased dopamine release in microdialysis, nicotine self-administration, shows a decrease in motivation to obtain sucrose. What I didn't mention here, decrease in the prepulse inhibition, which is a good hallmark of schizophrenia. And we've got several different plasticity measures that are all going with that we are really going after. BDNF is kind of the trigger to lead to downstream changes in other proteins, which we're going to target, including mTOR, including phospho-CREB, and even RS6 that we're actually starting to look at now. So these different cellular proteins that are downstream from that, to be able to look at mechanisms that underlie this, with the ultimate idea here is that, let's look at targets. Let's look at things that are changing in this model that are, relative to nicotine, that we can actually start to look at how to treat smoking cessation, because there's such a high amount of smoking in this particular in this disease, and obviously that turns out to be not only low quality life, obviously, but fatal. All right, I'd like to thank you. That's our soccer team. We play on Sunday afternoons. We're in the C League, which I call the championship division. C League's the lowest division. Okay, and we won our league championship a couple weeks ago, so I thought I'd throw that up there. And that's it. Yeah.
I did grand rounds on this subject on December 4th of 2014, basically kind of putting together some of the data that you're presenting,
Okay.
and sort of integrating dopamine to glutamate and learning, and how antidepressants and antipsychotics and drug abuse kind of fit together in one major pathway.
Right.
So your evidence, your data that you've been collecting from your rodent studies is supporting and corroborating some of the information I presented. But what's interesting is I think what your data is reinforcing is that the use of antipsychotics can help in enhancing learning. So ultimately, with BDNF as a downstream upregulated neuromodulator, what that's showing is that learning is really central for patients to get better, for your schizophrenic to get better, for your depressed individual to get better. So you can enhance it through chemistry, or you can enhance it when you couple it with psychotherapy, you get the maximum effect. So I think your study is really wonderful because it helps emphasize how psychotherapy may actually be helpful.
Yeah, I think that's a really good point, and that's something that I started researching learning and memory. So I always kind of go back to that at the end of the day. It's always the learning and the associations that are made. I mean, that's just critical to everything. It's critical, drug addiction, especially with nicotine addiction. Man, learning is critical because you've got these cues, you've got these things that it has to be associated with to be able to get it to work. It's like Palmetier said with the cocaine self-administration with rats. That's not hard to get them. There's not a lot of learning there probably. It's just like, hey, I can hit this and man, I feel great, right? I want to hit it again. With nicotine, it's a little bit more complicated, but it's still so damaging. So I think that's really something that we're going to look at other antipsychotics. That is one of the future work of our work is to also look at that in nicotine self-administration and to see if atypical versus typical do what they do in schizophrenics, because atypicals typically don't produce a lot of increases in smoking depending on the drug you're looking at. Haloperidol, though, is pretty defined as actually increasing smoking, so we're going to see if that increases their self-administration or affects it. Yep.
You know, I think it's interesting. I started thinking while you're talking, because we've had many discussions about this, that I wonder whether a model tells you anything about etiology of schizophrenia. And what I'm thinking is that, okay, so it's a quinprol is a dopamine agonist. So does that mean if this is it's a sustained effect, so exposure to quinprol early in development sustains this receptor sensitivity throughout life.
Right.
And it has a lot of features that look like schizophrenia. So if you expose the child to high dopamine, methamphetamine,
Sure.
at a critical period in development, would they lean to have those kind of schizophrenic behaviors? Which gets back to, again, if that sustained effect, when something's sustained, that means, okay, what happened? You've changed the expression of these proteins in some way that's sustained throughout life. So it's likely to be epigenetic in nature, in my mind.
Right.
Because the genes are already there.
Right.
And you're exposing them to a drug, so it must be an epigenetic phenomenon that's sustaining that increase.
Yeah.
And if that increase is passed on to the next generation, then it would be conceivable that somebody who exposes themselves at a critical period to amphetamine in one generation may be affecting them.
Sure. Well, yeah, we've already, Greg and I have talked about doing this as an epigenetic study. We're going to raise some to see if we get it in the second generation. So basically, treat animals in the immunoquinprol, do a behavioral profile is what we discussed, is like doing a prepulse inhibition test and see the ones that are the worst at PPI, is the individual difference. Make that male female, see if we get the change in increases in D2 in the next generation. Yeah, that's the way to go. I mean, if it's going at 2 years, it's sustained, you're getting all these changes. I mean, the thing is, we even get changes in BDNF and our quinprol saline animals in adolescents that are different than adults. So quinprol produces a drop in BDNF and NGF in adulthood, in the hippocampus, and they're pretty significant. But if you look at adolescents, just good grief, probably 30 days, 30, 40 days earlier, it's not there. Or at least it's not there in the same magnitude. So there's no doubt that those sustained changes. I mean, if you go on into later, we haven't even looked at later adulthood, like what it might look like there and what the changes are there.
So in that context, have you or Straba ever co-administered a dopamine antagonist, D2 antagonist, when you're administering quinprol?
No.
It's receptor mediated.
We looked at D2 antagonism in the cognitive impairment and
That's after it's already developed.
Yeah.
I'm saying, because
Right.
I was looking at the
No, not-
structure of quinprol, I don't know, maybe it's not working through a D2 receptor.
Yeah, it might be. But the problem if you do that, you have to probably mix the antagonist in with the agonist on the injection. I wouldn't want to get 2 injections. 2 injections, that's kind of a 1 day, 2 day old pup can be problematic.
It probably is a D2 receptor.
And the problem with the D2, yeah, when you go to the D2 antagonist, and which one you choose, they're not real selective. I mean, if we were looking at D2, D3, D4, but they're pretty selective relative to D2 versus D1.
There may be something unusual about D2 receptors that overstimulate them. I don't know why.
Sure, I know, yeah.
They would sustain the sensitivity all.
Yeah, it's a good point. It's like, you try to do this stuff and you're trying. One of the things that we did, that you and I talked about, but then we were wondering, it's like, well, what's causing this? Why is this happening? Why does this occur in these animals? And as I told you, it's like, well, I don't think NIDA is interested in funding that. I don't know if NIMH is interested in funding that. It's an interesting basic science question, and it's an interesting question that we could go after, and it may lead to something that should be really cool later on. But the problem is, that's not. Everybody just wants a model. Give me the model. But what you bring up is, that's be really interesting. Maybe there's some other way it's working. Maybe it is binding to something else. There's D2 receptors present at day 1. We know that that's the case, and they do change over those 21 days. They change all the way through day 60. And males really do this thing.
Did he ever take it out during development to see how far out
He did 21 to 35.
And it still worked?
Yep.
So what if you did 40 to 45 or something?
Yeah, I don't know.
How
Yeah. There's been, Henry Shuckman up at McMaster has done some work, up in Canada, has done some work with chronic quinpurol treatment. And he talks about it as an OCD model, which is really a stretch. But he'll go with the treatment. But he actually looks at he'll look at it chronic and then give them like, let's say 7 days. And then on that 7th day, they'll do a behavioral test and look at this checking behavior. And then they look at something that they claim is something is OCD relevant. It's a little bit of a stretch, but it gets published. So I guess it's going through peer review. But it's, I don't know. That's a great question. I mean, maybe if just chronic quinpurol for any period of time produces an increase in D2 sensitivity. So you can just manipulate what you do.
But amphetamine doesn't do that, right?
No, I think amphetamine really different regulates those receptors. Of course, the amphetamine, that's a different animal.
Well, yeah, but it's...
That's turning the dopamine synapse inside out. I mean, that's like, so, yeah. So it's, all these have different mechanisms. I mean, quinpurol is very specific to that D2. So that's a good, I mean, it's interesting that, that maybe that would work if you get it later on. Yeah.
There's been some work suggesting a primary nicotine receptor deficiency in schizophrenia. And I was just wondering how you would integrate that with the D2 receptor sensitization model.
Well, we could, we've not looked at alpha-7, or alpha-7 is a big change now, seen before. After going into adulthood and looked at that. What's interesting about the nicotinic receptor story is that it tends to be downregulated. Not everybody shows it, not everybody's replicated that. And nicotinic receptors change really rapidly. They can go up really quickly, they can come down, they can desensitize fast. That's one of the reasons why you put nicotine on board, it binds to the receptor, it desensitizes really fast, and then they upregulate. We actually got alpha-7 upregulation in early adolescence. Now that may seem like, well, that's an inconsistency. That's terrible. I put that in my grant, but I said, one of the things here, we don't know what those nicotinic receptors are doing early on in development. Maybe one really interesting change may be that if there's alpha-7 upregulation due to increases in D2 sensitivity, these things are interacting, that maybe that's one reason why they're, when they start smoking, that they get a bigger, change in dopamine release and all the types of things that go with an increase in dopamine and nicotinic receptors that may exist. So maybe they are actually genetically vulnerable to nicotine use. But I said, we just don't know. Nobody's looked at, as far as I looked everywhere, I can't find anything on what do nicotinic receptors look like in schizophrenia in early adolescence. But Yosef Tasavi and Kostreva published that paper in psychopharmacology. There's a big increase, about 100% increase in alpha-7 nicotinic receptors in striatum and hippocampus. Striatum was the biggest thing.
I just think what's really interesting is the role of the striatum and the nucleus accumbens, in particular in schizophrenia. And I mean, we know that there's movement disorders associated with phenotypically among schizophrenics, but what I find very interesting is now scientists are talking more about the nucleus accumbens and the striatum.
Yeah.
We see it clinically. The hippocampus, I'm sure you measure these changes in BDNF there, but the question is, so you're seeing the increase in BDNF in the striatum as well?
Yeah.
That makes sense.
Yeah, it was there as well. Hippocampus is, most of the studies we do with hippocampus were in adulthood.
So one question I have is related to the nicotine. You mentioned that it helps with anhedonia. Do you think that nicotine can be paired to help with some of the negative symptoms for patients with schizophrenia?
Possibly.
A short course of nicotine.
Yeah, you could do it. Well, you could do nicotine patch.
Yeah. So, and if you pair it with some sort of learning.
Yeah, I did. One of my first grants, I was looking at brain injury with nicotine and looking at how nicotine could be treat brain injury, and I was skewered on those reviews, to be honest. We'll probably reveal too much there, but yeah, we were skewered because they basically said, "You're saying smoking is good for brain trauma patients." I'm like, no. I'm talking about nicotine patch. So it got, you know, it was later on in the 2000s that started to be more of a thing, like, oh, maybe we can give them a patch and that can work. We're not, I wasn't saying smoke, I was saying, you know, nicotine is, I mean, it's a cholinergic agonist, so maybe it would work to do that. So.
Has there been any literature on the role of coffee and adenosine receptors in terms of brain anemia?
Not, there may have been, but I don't know it. It's outside of my realm of knowledge.
It's not so addictive.
Right, sure. All right, thanks a lot. Yeah, that's fun. Let's see. All right, you too.